Hey everyone, welcome back to my channel EduVibe. In today's lesson, we'll start with another topic of the electromagnetic radiations, and we're today doing the diffraction and the interference, and we also include this in with the Young's double slit experiment. So this is very important experiment, and this is very important experiment, the diffraction part, and we use that in the next lesson too. So this is an important topic, and you have to know about this. What is diffraction? What is interference? And what all this experiment, all the Young's double slit interference experiment. This is from the interference experiment, and this is where you have to know about how the diffraction can be occurring and what type of the diffraction we have. So let's start with the topic with the diffraction and with this one principle of the Huygens doubled developed the model of the wave theory. So we doing the wave theory model in the starting lessons, and that describes the motion of the wavefront. Describe the wavefront motion. The wavefront consists of the many small point sources of the tiny secondary waves called the wavelets. So this is all the experiment of the Huygens, and this called that the wavefront consists of the many small point sources. There's a very small point sources like this. This is a very point source, so tiny secondary waves too, which is all the wavelets, which propagate outwards and in the concentric circle at the same speed as the wave itself. The line tangent to the wavelets consists the wavefront. So you can see they made the very much like of the concentric circles. These are the concentric circles, and they made the tangent wavelets, which is the wavefront. And this is also known as the Huygens principle. Essentially, that what Huygens principle boils down is that the point on the wavefront will continue to propagate in a straight line away from the source of the wave in all directions. So this propagate that this straight line where the source can be there, from the straight line they will move on to all the directions. You can see that this moves on to the all the directions like this, and this, all the way to the strength. And this is the topic, the code when this principle like develop, this will lead to the development of the diffraction term. So diffraction can be taken by the Huygens principle, and further their principle and the diffraction can be denoted by the wavelength, and we because it all the things that how the Huygens principle can be made with the anything else and made with the diagram. So we have the diagram, whole big diagram for this like this, and this experiment can be after lead by the Young's double slit experiment. So principle and diffraction, when waves go through an opening or around a barrier of some sort, there will be a bend according to the Huygens principle. So basically, they tell us that when the waves going from the opening, when there's a going from the opening, there's some sort of barrier, and that some sort of barrier will take us to the band of something else. That band is telling about the how long, how short the wavelength is, about the all scenario of this principle. Under interference into a region of the geometrical shadow of the barrier or opening, this process is called the diffraction. When this occurring, that barrier will occur and that interference can be made, that region, that barrier, that opening is called the diffraction. So from here we get to know about the diffraction, that with the Huygens experiment we will get to know about what is diffraction. The medium does not change when we examine the diffraction. There is nothing that medium changes, like in the Snell's law or in the refraction. There is no any medium. Waves can diffract around objects. There is object and the diffraction can be occurring with that, and they all with the waves. The longer the wavelength, the more significant the diffraction bending of the wave. You can see here. You can see there is a less bend. There is a less bend of the waves, so you can there is less bending, and this is has the shorter wavelength. And you are seeing there is a more bending. There is a very much more bending. So this means this is a longer wavelength. So the wavelength is directly like all compared to with the how the bending of the wave can be. If the less bending, you get the shorter wavelength, and with the more bending, you get the longer wavelength. So this part is also including a diffraction with the Huygens principle. And the main point over there that waves can also deflect through the openings. If there's an opening, there's also can be deflected. So the smaller opening, the greater the diffraction. Ideally, the wavelength of the wave should be around the same width as the aperture. So if they have a smaller opening, have a very small opening, so we have a very greater diffraction. So there is a diffraction occurring, and this is also compared to diffraction part 2. If there is a small opening, so this is greater the diffraction. Narrow opening, small opening, you will get the greater diffraction. And if there is a very like wide opening, so you have a nearly straight kind of wavelength. So after this is divergence experiment which telling about the diffraction, and then there's a Young double experiment which is further can be do with the experiment, which is like uh, you can see the screens. The screens can be, if you want in the cinemas, that screen has some sort of diffraction can be occurring. So that's why you can see the picture directly on the screen. So that distance, that all the things can be do by the Young's double experiment is also connected to the diffraction part. So what they tell about that? In 1801, the Thomas Young performed the famous double-slit experiment, which provide the strong evidence for the wave model of light. So we're now doing with all about the wave model of light. Previous lesson we do all think about the particle model of light. Now we're doing the wave model of light, and we furthermore with this in the upcoming lessons. So what they call Young shown a beam of sunlight that has split by a placing a small card 1/13th of an inch thick in the path of the sunlight. So you can see that this is the like path they use. This is the trough and crest, which are the part of the graph where we can make the wavelengths and the frequencies. So that they do, they shown beam of sunlight in the placing with the small card, which is 1/13th of an inch thick, and there's a kind of a path of the sunlight, which is that this whole path. So by slitting the sunlight into the separate beams, this generate guaranteed the two paths were in phase as they were the more from same source. So you see there is a dot over there and this over there, and they go into the two paths. The light will go into the two paths. This was equivalent to the having the light pass into the two slits. And this is also this is the two slits, not the paths. We can state that these are the two slits in this. One slit and the second slit. So we are denoted this by the slits of the path. And then they made the like concentric circles. They both itself made the concentric circles, and we can say that they move this picture to the screen. You're not like doing that too much with this. You have to just know the formula at the end. But this is the thing that you have to know, that who created this experiment. And you have some know about this some sort of theory from this. Like as the wave passes through two slits, there creates a 2 point sources where that generated the wavelets. The wavelets which Huygens principle can be defined, that they developed that model to control property forward in concentric circles. So they will start the Huygens principle will tell that diffraction, and then further the Young's double slit experiment can tell about that when wave passes through two slits, the 2 point sources wave that generate the wavelets, which are the continue to propagate forward to the concentric circles as we made in this. This is all the concentric circles they made with that two slits. That's all the Huygens experiment tell you about. And there's a, from here you can see there's a two interference too. So these wavelets interface with the each with the two possibilities. There are two possibilities after that, that what type of screen, that how much like bright, how much dark light you will get. So there's the first one is the concentrative interference. So the amplitudes of the add together to make a wave with the higher amplitude, that is the brighter. The amplitudes add together. The amplitudes when they add together to make a wave, they have a higher amplitude, and we get a brighter image. Then we have the brighter like a bright light. And destructive interference is the amplitude that add together to make the wave with a smaller amplitude, and we get a dimmer kind of light to cancel each other out if they are equal in amplitude and the orient opposite to one another. So that's all you have to know, that concentrative interference has the brighter amplitude and the higher amplitude, and the destructive interference has the small amplitude, that is the dimmer. That's all you have to know. On a distant screen, you notice that the interference pattern consists of the central bright spots. Then you can see these are the bright spots over there. These are the bright spots. And these bright spots have different terms to be known. So that Young-Slit experiment further can be doing with that alternate dark and bright spots on both sides of the central maximum. So what are central maximum? These all are the terms we use in the further formula we do. And after that, they will tell that the bright spots and the dark spots have some type of term. So the bright spots are on the screens are the maxima, which are the regions of the conservative interference, and the difference in the distance from the two slits of these points in an integer multiple of the wavelength, such that the waves arrive in the phase. These points are also the antinodes. You are not doing like too much theory in this. You have just know that there are two spots. They are the bright spots. They are the dark spots on the screen. We have a maxima called the bright spots, and we have dark spots which called the minima. And we have a conservative interference in bright spots. We have a destructive interference in the dark spots. At the end, you have to just know that these points are also referred to antinodes, the brighter spots, and these points are also known as the nodes, which are the dark spots. That's all you have to know in this, not anything else in this, because these are not like very theory much part in we do in this. We do some the calculation part more in this. So mathematical equation. So we all do in the things that these are the like bright spots or the dark spots. These all things. These all are these all that spots we have that in a infinite amount of things. That this is called the central maximum. Then we have a first maximum. Then we have the second maximum. These all are the parts of this. First we have a like central maximum, then we have a first maximum, then the second minimum, then we have a second maximum. But we also know about the maximum and the minimum. These are all have the n values, that if they mention that you have a first maximum, so this n is equal to 1, because we use that formula when we have that n2. And this is like a some sort of screen we have, and the length, this is the length. So distance between the slits and the screen, these are the slits, slit 1 and slit 2, and these also are the two sources of light. And we have that L to all the distance between the slits and the screen. That D, we have this is a distance between the sources, and with this in meters. H, that H is a distance between the central maximum to the nth fringe. There's always central maximum, which is n is to 0. From the central maximum, we can if we want a distance, so we have from the like this all the x, that central maximum to the any nth fringe is n1, n2, anything which is in meters. And when we make like lines, this s1 goes s1p path, this is s2p path, and this is d2 straight, and this is goes over there. So this is some sort of like theta is angle can be made. So this angle is called the angle of diffraction to the n. There's the n's, so angle of diffraction to the n is called the theta. We have this one. So these are all the terms, and we use that all terms with the formula, and this is the formula for to calculate the anything. So firstly, the path difference. If you want to follow path difference and how the path difference can be, so you can make this by the s1p minus s2p, which is the absolute. So this formula you can't use in this, but you have to know about this. We are not using the destructive interference dart fringes anymore, because we can't use this one. We only use the conservative interference bright fringes more in this. We have to use this formula only, which is wavelength is equal to d times sine theta upon n. And we have one more formula to the shortcut formula we use in the previous lesson, but we have to know follow both formulas. But we also deal with the conservative interference, not with the destructive interference. So the wavelength of the monochromatic light in meters, wavelength. D is the distance between the two slits. Theta is angle of diffraction to the nth fringe, and the n is the fringe order, no units. And this has the no units, and has the no units of anymore. The fringe order is just a number to label the fringe. The central fringe is called n is equal to 2. The first order is n is equal to 1, and second is the n is equal to, and so on. There's an infinite amount of this. So we have just used this formula, and we have that formula to be known, and this is in your formula sheet, and this is one shortcut formula, as I told you, that we use in the upcoming lesson, in the next lesson. So we have one example from this, and this example is very like all we have introduced with this. So they mentioned that blue light of 460 nanometer incident to the two slits that are 0.55 mm apart determine the angle of diffraction for the third bright fringe. So they mentioned there is a third bright fringe, which means you have n is equal. And then we have the wavelength. This is the wavelength, so 460 nanometers. This is your wavelength, 460 nanometers. And we have a 0.55 mm apart. So which is the D you have, which is 0.55 mm. And you have to find the angle of diffraction, which is the theta. So theta is equal to D times sine theta upon n. And you find the sine theta, which is equal to the n wavelength upon D. So theta is equal to sine minus 1, reverse of this, n is 3, wavelength is 460, and nano has a value of 10 raised to minus 9 meters. And we get the D of 0.55, this is mm, and m has the value of 10 raised to minus 3 meters. And this is your thing. And when you solve this, you get the theta of about 0.14 degrees, which is your value for this. So from this, you can come to know about how we can use the formula. And we do more examples when we do the practice questions. And for now, this is example, and this is like the end of this lesson. So you have to know about this INV thing, and we do one more thing in this in the next lesson. So let me say where EduVibe, learn smarter, not harder. Please like, share, and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till let's get it with EduVibe.